Since the early 1990s, we have discovered thousands of exoplanets, planets that orbit stars beyond our own sun. But for most of these planets, we typically only know their size, either their radius or their minimum mass, and how much radiation they receive from their star. If that amount of radiation is similar to what the Earth receives from the Sun, we say the planet is orbiting in the classical habitable zone. The classical habitable zone is where the Earth can support liquid water on the surface. If our planet was too close to the Sun, our oceans would evaporate and we would dry out. Likewise, if we were too far away, we would freeze. On geological timescales of a few million years, the Earth can moderate its surface temperature within the habitable zone by changing the level of carbon dioxide in the atmosphere. Carbon dioxide is a greenhouse gas that can trap the heat the planet receives from the Sun. The more carbon dioxide in the atmosphere, the warmer the planet. The Earth controls the level of carbon dioxide by the carbon cycle. Carbon dioxide in the atmosphere dissolves in rainwater and reacts with the rocks on exposed land to create hydrogen carbonate. This process is called weathering. The hydrogen carbonate washes into the oceans and carbon becomes trapped in solid sediment. This ultimately returns to the atmosphere via volcanoes. Weathering occurs faster when the planet is warmer, acting to reduce the amount of carbon dioxide in the atmosphere and allowing the planet to cool. On the other hand, if the planet becomes cold, the weathering rate reduces and carbon dioxide can increase to trap more heat. The carbon cycle has varied the amount of carbon dioxide in our atmosphere over our history to maintain our oceans. So long as the Earth or an Earth-like planet is within the habitable zone, the carbon cycle can act as a thermostat to maintain a comfortable surface temperature. Without the carbon cycle, the Earth wouldn't be able to moderate its temperature, even within the classical habitable zone. Planets very different from the Earth have no guarantee of maintaining water in the classical habitable zone. Both the Moon and Mars are inside the habitable zone, but they do not have carbon cycles, are too small to retain a thick atmosphere, and have no lakes or seas. The other Earth-sized planets we have discovered may be nothing like the Earth. They might be in the classical habitable zone, but have very different geology, chemistry, or atmospheres that might not allow liquid water to exist. But what if we did find an Earth-like world? Would it be exactly the same as our own? What if our new Earth had a carbon cycle, but less or more water covering the land, which changed the rate of weathering? Or what if the volcanic rate was slightly different, or the planet was in a different place within the habitable zone? How Earth-like would our Earth-like world really be? The effect of these tiny changes to our own Earth-like planet are what you can explore here at Earth-like. And if these Earth-like worlds are so different from our own, just imagine how diverse planets can really be.